למה זה... ראשית זה עובד, אבל... מה קורה כאן? טוב, עכשיו נעשה שוב. מוזר. לא, לא, לא. אני הולך. אני הולך לשנות את ההגדרות מסך כאן, כדי שיהיה לי יותר נוח. טוב, אני מוכן. מה? כן. כן.
mais je t'ai dénoncé, j'ai même été toute seule. Il y a ma petite fille.
Ah, aujourd'hui. Okay, so thank you all for coming. We decided to start the seminar series on Sunday mornings. ELSEC faculty will have what we call faculty meetings, which are research meetings given by ELSEC faculty to ELSEC faculty. We decided to keep the time, but to keep also the format for lectures given by ELSEC faculty, but to extend until the teaching year will start. We're going to make these meetings public. So the events are going to be open to everyone. Students, postdocs, anyone else who wants to attend. And since this is the first meeting and the notice was short, I decided to take that slot, okay, so that people not coming here today will feel bad for the future meetings, and there will be high chances of them coming. And also I decided to give a presentation about a subject which is not at the center of the research in my lab. This is a collaborative work that I did with Vani Rajendran and Jan Schnupp. Jan is at City University, Hong Kong, and Vani was a postdoc at the time, was a postdoc in his lab. She says now she just got a research position at UNAM in Mexico. And the story was about surrounding the issue of dancing. Not really dancing, okay, you will see. So we would like to know about dancing, okay, but this is a very rich subject with many different levels. And us as system neuroscientists, we can provide information about dancing only through some limited perspectives. Okay, so for example, in musicology, you are going to study dance, for example. There are many things that you are going to do with dance, but one of them is studying dance as a cultural phenomenon. And then there's a whole field for music cognition. So, for example, in music cognition, you are going to study musical mechanisms that shape beat induction. I'll say a word about beat induction in a moment, but beat induction is basically the process that creates the steady rhythm, okay, in your head, because it's not always in the music itself. And then, more generally, in cognitive neuroscience, you can ask questions that have to do with this sensory, auditory, motor synchronization. For example, Merav Achisaar, who was not here, studied the relationship between the ability to tap to a metronome and short-term memory. And finally, we get to systems neuroscience, which is us. Okay, so we would like to have animal models, and we would like to ask questions about things that are within this range of phenomena, okay, and that can be asked at the level of animals. And this brings me to the Einsteinian dilemma. Is, I mean, it's not, that's my way of saying it. This is an actual quote from a letter of Einstein to Max Born about Beethoven symphony, describing Beethoven symphony as a variation of wave pressure. Okay, so the question really is at what point we reduced things to such a level that they become nonsense. Okay, and that's a question that I would leave to you, okay, at the end to judge. Okay, so let's go to dance. So here's a very stylized and sophisticated dancing. Okay, what I want you to notice is how well they are timed. Okay, so the music is, this is Prokofiev, it's from Romeo and Juliet, that's part of the, what is called, a neshef, the ball at the mansion of the Capulets, where Romeo and Juliet meet for the first time, so that's the background to the story. But the point here is that given the music, these guys synchronize extremely well to the music. Okay, but that's not only in, you don't need to be a ballet dancer. Okay. Now, notice, I mean, these two guys obviously trained a lot, but not this woman or that one, okay? They are moving also to the beat, although they didn't train, okay? So that's dancing and audio motor synchronizations are extremely strong and very natural and immediate in humans. Now, it turns out that this is true also to some animals. Okay, so this is a famous kakadu called Snowball. So, the owner of Snowball posted these movies on YouTube, and some researcher in music cognition got interested by this. Okay, so there are two papers about Snowball, in both of them in current biology. I'll show you one of them, about the ability of Snowball to dance. But the fact that there are two papers about one kakadu, some 6 years apart, tells you that this is rare. Okay? It's not every animal, it's very rare. And there are, I'll tell you a few words at the end what people think about that. Okay. Now, when we talk about dancing, there are two interesting facets here. One of them is this issue of beat induction. Beat is an internal structure that is not necessarily always in the music itself, or not directly in the music. You don't need to have energy at the time of the beat in order to beat to get formed. Okay, so the process of the generation of an isochronous rhythm inside yourself, which is induced by the music, but not necessarily exists explicitly in the music, this is what people call beat induction. Okay? And then you have this periodic predictive audio motor synchronization, which is the thing that we need in order to dance. Now, I'm going to bypass the issue of beat induction. We don't know whether animals show beat induction. There are some evidence that yes, some evidence no. The whole thing is a bit in the air. And so in the experiments I will show you, we bypass the issue of beat induction. This is done in all animal experimentation that has to do with these issues by providing a constant metronome. Okay, so that's reduction, huge reduction number one. is I'm not talking about dancing anymore, to music, I'm talking about moving to a metronome. Okay, so this is the question. Is periodic predictive audio-motor synchronization possible in animal models? Okay, now, it turns out I'm going to do now a second reduction, okay, and that's the fact that instead of dancing and moving the body and all of these things, okay, the model for studying predictive movements is tapping. So what I'm going to ask, I'm going to do an experiment with you. Put your finger on the table. Okay, I'm going to play a metronome, a sequence of constant rate clicks, and you should tap. Okay, in synchronization with the metronome. Okay, so I'm going to play it now. Okay, you all perfect. Without training, all of you did it very nicely. Okay, that's the point. Okay, this doesn't happen in animals. No animal does it like that. Okay. Now, in order to synchronize to the beat, to be able to tap at the beat, you want to bring your finger down at the beat, exactly at the beat. The movement has to begin before the beat. Okay, so that's the predictive aspect of it. We talked about what a negative mean asynchrony. Okay, that's a complicated way to say that we tend to move the finger before the sound. Okay, and this is taken, the measuring negative mean asynchrony is taken as evidence for predictive movements. So this is how it looks. This is from a paper, this is an illustration from a paper of Amos Bosson and Snoring Renault. So this is just an illustration. You have two onsets of the sound. Okay, the one sound event and the next sound event. Okay, and what the illustration is attempting to show is that the finger, in fact, the finger falling down, okay, the hit of the finger on the board that measures the tapping occurs slightly before the sound onset. Okay, these are EMG measurements that Amos did with the help of Output. Okay, and the finger flexor is what brings the finger down. Okay, the finger extensor is what raises it. Okay, and again, the point here is that the finger flexor, okay, the movement down, okay, starts well before the next sound occurs. Okay, so it is generated, it is triggered by the previous sound, but it is locked in time, or at least the subject tries to lock it in time to the next beat. And that's a predictive aspect of it. So predictive motion is very common in humans. It has been shown in some particular animal subjects. Okay, so that's the first paper on Snowball. Okay, experimental evidence for synchronization to a musical beat in non-human animal. Okay, now you will see a lot of these plots. So these are phase plots for the time between one beat to the next beat in the music. So 0 is the time of the beat, and then time goes like that, like that, like that. This is the middle of the interval between the two beats, and then it goes back to 0. Okay, yes?
When you say that you don't see it in animals, is it for auditory stimuli or is it in general?
I will say something about that in the next few slides. So this is Snowball performance. Snowball, this is for the head bob. Okay, you saw it doing like that. So these are the times of these head bobs, and they tend.
How is the time defined?
What? How
is the time defined? It takes time.
So they use actually pieces of music that Snowball liked.
No, I meant in terms of the motor action.
For the motor action?
The motor action itself takes time. So what is the time point which is considered?
This is the onset of the bob. So it's the moment in which it starts to lower the head down. The point here is that you have a fair number of events that have negative phases. Negative phases are the phases that precede the sound event. Okay, events that occur above time zero, positive phases would follow the sound event, and these are events that precede the sound event.
But if you have a random distribution around zero, you will have some negative.
No, so first of all, you show that this is not. They show that this is not random.
No, around zero.
A random distribution around zero, but that's already predicted because they need to know where the zero is going to happen. Random distribution around zero is good. Okay, that's acceptable. I will skip that. Okay, the point was that there are stretches of time in which Snowball. This is 1 minute worth of music. And these are the time between successive head bobs, okay? And it didn't synchronize the whole time. It was doing some random stuff. Here it was a bit faster, okay? And then it catches the metronome for a while, and then again it loses it, and then it catches it again. So that's the behavior of Snowball. Okay, now that's a paper in Primate. So this is work from the lab of Hugo Merchant in Mexico, in UNAM. And they tried to teach monkeys to tap to a metronome. It worked. And I'll show you the final results. But it took them many months. And it turned out that before they learned how to tap to auditory stimuli, they had to learn how to tap to visual stimuli. Okay, so they taught them how to tap to a visual metronome. You can see the performance of the, again, plotted in the same way. Okay, so this is human data. Humans tend to precede time zero very clearly, both for the auditory and for the visual metronomes. Okay, the distribution of the beat time is at negative phases. Primates synchronized, but in a kind of an idiosyncratic. These are macaques, okay, not simply primates. So macaques synchronized, but they tended to do it at idiosyncratic phase, okay, so not necessarily at time zero. And they did it less well for auditory than for visual metronomes. And as I said, they had to learn, it took them 8 months to get the monkeys to tap to auditory metronomes. So the first 6 months they were training to visual and so on.
So why it's predictive? Why it's not?
Here it's not necessarily predictive.
No.
Okay, it's synchronized. What I'm saying here is that it's synchronized.
Maybe it's the previous one.
Maybe, yeah, it's always triggered by the previous one. Okay, but the new algorithm, and it's synchronized. Okay.
But in general, when do you call it predictive?
What?
When do you call it predictive?
That's the center point of my talk. Okay, how to measure, how to actually show that things are predictive.
How do you train the animals? I mean, what's
So they had a number of different ways of doing it. In this case, I will show you at the end what Vang and Jan did was to actually get them lick. When they did the lick at the correct time, they got a drop of water immediately. In these studies, there was a fixed sequence of 6 beats, and the animal has to do, I think, the last 4 correctly or something like that, and then it got, at the end of the trial, it got a reward. But the question is well taken. Okay, that it's not easy to.
There are many experiments in which animals are trained to produce a particular duration.
That's not the same thing. Okay? And the proof that it's not the same thing is the fact that they could switch between 2 intervals. Okay? The animal followed the interval that it was given. Okay? So it really synchronized to the interval. It's not that it produced a fixed interval.
No, animals, monkeys are trained to produce an interval, so there are 2 stimuli and they have to generate, to leak or
yeah, I don't know. I mean, there are many ways. I'm telling you how this was done. Okay.
So you use different intervals. They use different intervals. But what's the kind of range? How much
Okay,
time
so
is
the range, yeah, I should have said that the typical range for humans, okay, the best locking for humans is between 2 per second to once every 2 seconds. Okay, from between 2 hertz and half hertz, or half hertz and 2 hertz. And most experiments in animals, animals use that range too, because they want to have animal models. Now, in order to get the animals to actually synchronize to the event, okay, they developed a second way of doing it with feedback. So here the feedback was on the sensory stimulus. The reward was always at the end of the sequence, but when the animal hit correctly, the stimulus went on until the animal made the action, the task, and the animals learned how to shorten it to make it as short as they could, okay, and then they learned how to synchronize on the beat, okay? So these are primates. So they can do it. They do it pretty well. There are YouTube movies, I think, showing the animals tapping, but it is not easy. Okay? It's not easy on them. Okay, so we really want to have a model, a rat model, a rodent model. Okay, so that's a model. This is a paper that came out almost exactly a year ago. So that's from the lab of Hiro Takahashi. And what they tried to show is that what they showed is that rats, when you play the music, they tend to do some head movements that are locked to the music. There was a huge amount of media attention to that paper, okay, it was rat dancing and the music of Lady Gaga and all kind of things like that. The rats habituated very fast. So the common understanding of this result is that these were starter responses. So the animals got moved to, were activated, were moving because of starter-like reflex. And usually after one repeat or twice, two repeats of the same music, they stop doing it. Okay, so that was in this paper, and this is also the experience of other labs. So we are not sure that they really dance, but this is a paper in which the rats were, again, trained to produce regular rhythm, only here they were allowed, so again, these are these phase plots, okay? The gray lines show you the time window at which the animals were allowed to make the movement, okay? So they were allowed to make the movement starting here and ending here, okay? Each symbol here is the mean time of the action of one of the rats that they used. So the rats did the action, but they did it within the allowed window, and they did it periodically, but they all had positive mean asynchronies. Okay, so these data can be interpreted as the rats reacting to the events rather than predicting the events. Now, the task designer was such that it allowed the rats to react because they had a very long window at which they could make the movement. And so the question that Rani and Jan wanted to test is whether what happens if task design doesn't allow you to react. Okay, so what I want, I get here now to the heart of the story. Okay, we went from dancing to tapping, from tapping in human to predictive actions in rats, and now the question is whether rats predictively time their action to the metronome. Okay, so we have a paper in bioRxiv, it's under review now, and here's the task design. So at every trial, there was 16 bits of a metronome. Okay, the interbit interval was selected randomly between 0.5 seconds to 2 seconds, so between half hertz to 2 hertz. And the rat had to leak, okay, and it got a reward under two conditions. First of all, one condition was that it did not leak in the previous 450 milliseconds. And the second condition was that the leak, when it occurred, was very close to the metronome time. So within 15% of the metronome time centered on the metronome. Okay, so 0.75% of the metronome period on each side of the metronome time. Now, rats tend to leak in bursts. Okay, bursts of about 7 hertz. Okay, that's they do everything in about 7 hertz. This is this very, very strong central pattern generator that we have in the brainstem. So they breathe at that rate, and they whisk at that rate, and they also leak at that rate. It's the same central pattern generator. So the behavior consists of bursts of leaks separated by pauses. Okay, and because the bursts are at 7 hertz, okay, it's in fact it's the first leak of a burst that determines whether it is rewarded or not. Okay, because that's the leak that occurred after a longer interval. Okay, the next leaks in a burst are at 7 hertz, so they're 150 milliseconds apart, so they will never be rewarded. So that's a typical raster. Okay. There are here 45 trials, which was about a typical number of trials that a rat did every day. Okay, everything here is in normalized time, so these trials had different rates, okay, but they are all stretched or squeezed to a common time scale. So I'll talk a lot about phase. I'll show you a few plots in which the x-axis is in time. Most x-axis will be in phase. Okay, and the rats obviously don't leak periodically. Okay. Now, this shows all the leaks. So on the next plot, this is exactly the same data, but with two changes. First of all, I plot only the first leak of each burst. And secondly, you can see here the leaks that occurred within the reward window. They are in blue. Okay, so these are the leaks that got rewarded. And if I just plot the rate of the leaking around the metronome times, okay, it looks like that. Okay, so yeah.
If you just plot all the leaks in black,
you see a similar
without the lines, is there a pattern that we would visually identify? We would see.
No, and the reason is that this is a relatively small modulation. Okay, you can see all the numbers. Okay, so the average here is about the unit. It's about the probability of 0.035. Okay, and the modulation is about 10% of that. Okay, so there is a tendency to leak around the time of the bursts, whether predicted or not, we'll see in a moment. Okay, but certainly the modulation is not very strong. Okay, so to the extent that rats dance, they don't dance very powerfully. Okay, but the question of predictiveness is still there. Okay, so what Vanya and Jan did next was to take all of these plots. What you see here is the average period histogram of the leaks. Okay, again, roughly the numbers that I told you. You see the individual animals and the average, and they tested. They showed that there were the increase in leak rate preceded the time of the beat. Okay, so They consider this as evidence for predictive leaking. Okay, and so
But the time was random.
what?
You said the intervals were random.
From trial to trial. Okay, within trials they were fixed.
What is a trial?
Okay. Trial is 16 bits.
Oh, okay.
Okay, so within the 16 bits the rhythm was fixed. Okay, and then
Eli, the intertrial interval is random? Intertrial.
the 4 to 5 second silence were
Okay,
random.
so go back to the next slide, because you have a very nice response. Next one. One more. You have a very nice response also to the first click, okay, which is very similar to Olav.
Yeah,
The first
okay.
one cannot be predicted.
Yeah, you're right.
And similarly, you would
In a
expect
moment,
that-
but
you
in a
would
moment you will see why, okay?
You would expect the last ones to be better.
Maybe, that's not, this depends on the rats, okay? They could either,
He has to learn during the 16.
yeah, but the question is how fast is this learning, and this is not something that we could, or that we try to determine here. Okay, so this, that was the state of the project in just before COVID.
Eric,
Yeah,
the window of reward started before the beat, right?
just before to just after the time of the,
So is it, so the fact that there is a little bit before, rise before the beat, is that really showing prediction, or is this showing the learning of the task?
well, to learn the task, they need also to learn to predict because this is in phase, okay? So for different trials, this is different times. That was the argument, okay? The argument was that the animals are, the task design is such that it encourages the animal to lead before the metronome. So, but in order to use the opportunity to get to go before the metronome, they need to be able to predict when it will occur.
Because when you started with humans saying that the movement starts before the tap, that has a reason. Right? The reason it started before the tap is because you want the tap to be on the beat.
Yeah.
Here, this is not the case, right? There's no issue of starting the movement before so that it will be on time.
They don't, in principle, they don't have to if they want to synchronize, okay? But in this task, okay, the point was to push them to predict, okay? To see whether you can get predictive movements in animals.
You don't get more reward for prediction than they do for being right after.
They don't, but I mean, this is a subtle point, okay? The subtle point is that the interval is so short that if you don't predict, then you can't hit the right after, okay? The reaction time is longer than the time window that is allowed. Okay? So we submitted the paper, okay? I helped them a little bit with the data analysis, so I got middle place in the list of authors. And then the paper got submitted, it came back with 5 reviews. Okay, 2 were very good, 2 were a bit wishy-washy, and there was reviewer 5 that sent us the whole thesis, okay, with MATLAB simulations and everything. Can you guess who reviewer 5 was? You know him, many of you know him. It was Nor Jacobi. And he said, this is not evidence for predictive leaking, and to support his claim, he showed the simulations. Okay, that's the result of simulations. Okay, where you have 2 models. One of the models, these are simulations. So these are the data from the paper. These are simulations. Okay, blue line is from a model that obviously has prediction, and the red line is from a model that obviously doesn't have prediction in it. Okay, so what are the models? Okay, for the predictive model, what Nori did was by hand extract a kind of a shape that was similar to the shape of the changes of the leaking rate that were estimated from the data, okay, this thing. Okay, so he just drew some lines that roughly had the same shape. Okay, the time of the event is after the beginning of the increase in the leak rate, and then you get a predicted leak rate for the process. You generate Poisson leaks based on this rate, and you get you get this. Okay, you get the blue line. Okay, that's obvious. For what we call from now on the reactive model, it was actually much simpler. The idea was that after every leak, the animal suppresses its leaking for a while, and then it goes back after a fixed time that is independent of tempo. It goes back to a constant leak rate. Okay, so it does something that's locked to the metronome. Okay, but that thing is not predictive. Okay? It just suppresses for a while its leaking rate, and if you just do the same thing, you get the red line. Okay, so you get something that looks very similar to our results. Okay, the paper got rejected. We sulked for a little bit in our offices. There was COVID, and at some point, I started working with Vani trying to answer this critique. Okay, so the first thing that I did with her was to actually break down the data by tempo. Every trial had a different rate, okay, but here we just bunched all the trials into bins, 5 bins, okay, and you see the firing rate, the leak rate around time 0, around the metronome time, for the slowest tempi and the slightly faster and so on. These are the fastest tempi. Okay, so one thing that we saw is that the mean onset asynchrony seems to become more and more negative the slower the rhythm is. Okay, that's, I will not go into it, but that's actually a good result. Okay, that supports the idea of predictive movement, but this was not enough. Okay, so we wanted to quantify these observations in a bit better, and for this we used a simple Markov process model for the leaking process. So the process can be, the rate can be either during a burst of leaks or during a break between the leaks. It can be in each one of these for a while, okay? And these things come successively. So there's a break and then a burst and then a break and then a burst and so on and so forth. And the point was that by manipulating the probabilities of progressing along the time inside burst or time during break, okay, we can learn a lot about the process that the animal is using in order to during behavior. So again, the whole what we can take a trial, okay, and take every, let's take 10 millisecond period during the trial and mark it as a break or a burst. Okay, and then by the successive point that it is within the break and the burst, we get its position within the chain, okay, each one of the 2 chains. Okay, and the Markov assumption allows us, if we assign probabilities to these transitions, okay, the Markov assumption allows us to compute the whole probability of those sequence simply by taking the product of all the probabilities. So the crucial thing is how do you assign probabilities to the transitions? In principle, this structure is very rich. I mean, we can, by selecting different probabilities to go forward, to go backward as a function of time, you can mimic many distributions of leak and burst times. In practice, it turned out that parametrically, we simply use fixed probabilities to go forward, okay, and a fixed probability to go back to the complementary probability to go back to the first state of the other type, okay, and we estimated these probabilities. Okay, that's, if you want later, I can answer the question of why we did that. So we have the simplest model doesn't care about anything, okay? It's just an alternation of bursts and leaks. We call it the insensitive model, okay? The rat doesn't care about anything, not about the metronome, not about the water, okay? Next, one thing we realized is that if the animal gets a reward, the leak becomes longer, okay? So we break down, do you see these colors, faint colors? So these are reddish and that's greenish. Okay, so, sorry, it's clearer on my screen. And we could model the leak bursts where the first, they got rewarded, okay? Where the first leak was rewarded, we could model them with different probabilities of progression than the leak bursts that were not rewarded, that were short-term. Okay, but the crucial thing was turned out to be a different thing. Okay, we tried to model this idea of Nori that there's what we call a responsive break. Okay, so a time between metronome where the animal reduced its leak rate. Okay, and we parameterized that response, the time at which the brake becomes responsive. Okay, so one possibility was the Nori type model in which the brake starts and ends at fixed times after the following the metronome. Okay, so this is what we call the reactive brake. During the reactive brake, okay, the brakes were longer. Tendency to leak was lower. But we could also make the beginning, and you will see particularly the end of the brake, depend on the tempo. Okay? And when the end of the brake depends on the tempo, that indicates that the rate predicts the time of the next metronome. Okay? So the whole thing turned out that A here is equal to 0, okay, in the data. So the whole thing ended up by a test on the value of this number. Okay. And again, we ended up with 6 types of models. Okay, the insensitive model, which is baseline, we check everything with respect to it. Okay, a model in which leaks could be either normal leaks or rewarded leak bursts. Okay, a model in which there was only type of leak, but the brakes could be responsive or not, and a model that had everything. Okay, 2 types of leaks and 2 types of pauses. Okay, and these models with 2 types of pauses could be predictive or reactive. So first of all, turns out that the more parameters we put, the better the fit, and in a very strong way. Okay, so these are the log likelihood values, okay, that we got for the different models. Okay, the water sensitivity turned out to increase. This was one additional parameter which increased a lot the fit of the model. Okay, making pauses, responsive pauses, also increased a lot the likelihood of the model, and making them predictive increased it even more. Now, each one of these jumps is by 1 or 2 parameters, and it increases the likelihood by hundreds. Okay, so that's extremely significant. Okay, there's no doubt about the significance of these results. What I show here are the period histograms broken to the different tempi. Okay, and the main point, like in this one, okay, the green line is the fit of the predictive model. The orange is the fit of the reactive model. Okay, so you can see here, and also there, that the predictive model is doing much better than the reactive model. So making the responsive break depend on the rhythm is important. Okay, and again, the model parameters tells us a little bit what's going on. The blue are the time of the responsive breaks when the rhythm is a bit slower. And if you look at the best parameters for the reactive model versus the predictive model, you can see that the animal increased the time, spent more time in these responsive break times at the longer rhythms. Okay, so you have less red here than here. Okay, that's the point. Okay, or if I plot it as function of time, okay, you can see that the rate was high for a while after the metronome, then it dropped down. Okay, so as I told you, this was insensitive to the tempo, but the jumping back to the higher rate occurred at a later time for the longer rhythms. Okay, so that's our evidence that the rats are predicting the time of the next beat. What time is it? Okay, I'm going to skip this this bit. Okay, just to say that in addition to increasing another thing that the rats did was that at faster tempi, the leak rates were shorter. Okay? So since the leak rate was shorter, they had better chance of catching the next beat. Okay, but this is not a predictive strategy. Okay, this is a kind of strategy that is independent of the tempo. Okay, it will generate more longer intervals at faster tempi, so that the animals can increase their reward rate, but it's not predictive. So we uncovered two rate-dependent behaviors. One of them is the predictive end of responsive breaks. Okay, return to higher leak rates occur later at slow rhythm, and a non-predictive lengthening of unrewarded leak rates at slow rhythm. So let's use a mix of predictive and non-predictive strategies to maximize the reward rate. Okay, that's important.
How do you know this is maximizing?
What?
How do you know
To
this is
improve,
maximizing?
it improves the, how do I know?
No, you prove that this is the optimal.
No, we didn't prove that it's optimal. It's a kind of obvious that it helps them to get, okay, I agree, okay? To increase the reward rate, okay? That would be better. Okay, so what? Okay. So first of all, it was fun working with the data were relatively high quality, okay, and the fitting of these Markovian type models turned out to be quite a lot of fun, and particularly because it ended up with a very simple statistical test for showing the predictiveness of the behavior. And now, more generally about dancing. Okay, so animals don't dance. Okay, the rats did not start to lick periodically or to do all kind of movements. There is one influential hypothesis in the field which is called the vocal learning hypothesis. Okay, animals who are vocal learners might be capable of locking to metronomes or to dancing to music. Evidence is snowball. Now it's very appealing in all kinds of ways because for audio-motor synchronization you need connection between the auditory and the motor system, okay, which is exactly what you have in vocal learners. Okay, so that's why the hypothesis is appealing. Okay, the evidence is not very strong. The other hypothesis, just a moment. The other hypothesis, which kind of counter hypothesis, is what people call gradual audio-motor evolution hypothesis. Okay, and our results, it starts with human can dance, and then primates are capable of one-to-one action-to-beat synchronization, as I showed you, if you train them hard enough. Okay, and what we add here is that rats do not dance. They don't do one-to-one action to tap, okay, but they do predictive synchronization. So that's another layer below, okay, that is necessary in order to, that might be part of the mechanisms that would lead eventually to dancing. And then the question is, why do humans dance? Okay? And there is one hypothesis, which is that dance is fun. Okay? Somehow dancing goes into the dopaminergic system, which releases dopamine, okay? And that's the thing that's special in humans relative to animals. That's still a hypothesis. Let me finish and then I'll take the question. Okay, so now what about the Einsteinian dilemma? So I told you about all kinds of things that we can do with dance at different levels of study. Here what we add is predictive movement in animal models. And as I said, okay, the question is whether by studying predictive action in rats, we reduce dance to nonsense. Okay? And again, I leave this as a question. I don't want to argue either way. Okay, and finally, this work was done with Vani Rajendran and Jan. Jan is an old colleague of mine. He moved a while ago from Oxford to City University Hong Kong. Vani was his postdoc. These are two undergrads participated. So Tung Yi participated in the collection of the data, and Yonadav here worked a summer helping us to program the optimization, the maximum likelihood procedure for the model. And this is Jan. The reason I selected this photo is not because I am with a jacket and a tie, but because this is Andy King, okay, who is the original reason that I know Jan. Okay, and the three of us wrote together this book, this textbook on the auditor neuroscience, and this photo was taken in summer 2018 when Andy was inducted to the Royal Academy of Sciences. So, and these are Jan and Vani in Hong Kong. Thank you. Okay, yeah.
Excellent. Now, rats and rock monkeys are social animals. They are capable of vocalization. To the best of my understanding, they don't sing as a group. They don't sing in symphony. Howler monkeys, for instance, are new world monkeys in Brazil, in the Amazon, and they howl together several times per day, naturally. So I would maybe expect that they would be capable of synchronizing their behavior accordingly. And maybe another reason besides dopamine release in humans is that dancing together trains you to hunt together as a group, which is something humans are capable of.
Yeah,
and if we
wolves and well, I wanted to say wolves don't dance, but actually I don't think anyone really tested in the lab whether wolves and lionesses dance or not, but I think they don't.
Yeah, so we need a rat-sized animal that we can house as a group in a lab environment, or at least with a virtual environment. So
I mean, animals who are very social and, for example, ferrets also don't dance. That's pretty obvious. So just being social animals is not enough, I think, for dancing. And there may be a lot of hypotheses of why humans developed this trait. But hunting is one possibility. There's a guy called Daniel, who's writing about evolution and dance and things like that, and it's interesting. Marmosets are New World monkeys. I don't think they dance, do they?
Maybe they do.
But
I don't watch them.
I mean, they do communicate vocally. So Didi, correct me if I'm wrong, but they sort of dual vocally. Okay? One vocalizes, and then the other one. What?
They do turn taking.
Yeah, turn taking. So, but this is not yet audio motor synchronization to an animal. It's not the same.
Yeah.
Yeah?
rhythms, it's always the case, the question which Asaf Preska studied at the time in his PhD, whether it's really synchronizing with the rhythm or whether it's sequential prediction of the interval, which is something that somebody alluded to before. That maybe even if you do see predictive tapping or predictive actions, they are due to the fact that you've learned an interval and you now memorized it. And now for every stimulus, you reproduce this interval without actually being anything predictive or synchronizing with the rhythm.
Well, producing the interval requires a kind of measuring the time.
Yes, so it's measuring exactly your ability to measure the interval, but it's not necessarily about the rhythmic part. And so what the sub did during our time was to measure.
You're right. I think these experiments don't resolve them. Okay, what the animal could potentially do is try to produce the previous interval exactly. Okay, I think that's correct.
The other thing is I was wondering whether the observation that many of us, sometimes when we sit, we kind of tap our, go like this, some people do it more, some people do it like this flutter that we do. Is this something that is seen in animals? I mean, this is also really actually producing an internal rhythm.
I think that this is actually much more prevalent in animals. Okay? You see animals doing periodic activities. You have all of these birds. You have birds doing courtship, dances and things like that. So these are periodic, very often periodic structures like that, but not locked to music.
Okay, so that is seen in many, like in pilot, they synchronize and so on and everything.
They don't synchronize, they produce periodic activity.
No, but they also synchronize. Animals synchronize with one another, right?
No. And that's the point.
But at least, not an ontologist, but it's in
Again, they can tune, okay, but they don't.
Fireflies.
Okay, but these could be reactive. They are not.
No, because
But
the
that was my
frequency
question.
changes.
That still couldn't be predicted.
Well,
Most of the movies about fireflies are fake movies. Okay? Be aware. Okay?
There was one study, I think 15 years ago, by former Fuji student, German Sumbre, a student of Benny, and there was no movement there, but what they did, this was in zebrafish, and they used visual stimulation. I don't remember exactly where they recorded from or where they looked at. And so the stimulus was periodic at different frequencies, and the response was also periodic. But the interesting thing was that the response...
There was one last response after the end of the sequence.
I think there were several, but I might be wrong, but the thing was that it was the same frequency of the stimulus.
Yeah.
So in that sense, it was predictive.
Yeah, well, we have... These are usually much slower than... we have these results in RATS too, including physiological recording. So if you train rats to link to regular rhythms, they would produce one last leak often, after the end of the sequence. This is associated with activity in auditory cortex that goes to motor cortex and seems to be necessary for this extra leak to occur. I hesitated whether to put this slide because I'm both on the paper. There are 17 Chinese authors and me. It was too much data. But these things could be the neural mechanism underlying this type of.
Everything is neural mechanism. Neural mechanism is everything. Neural mechanisms are everything.
You don't know.
No, maybe it's clear.
Many years ago, ago, Torsten Wiesel came to give a lecture in Israel. And I took him for a tour of Jerusalem, including to the Kotel. And at the Kotel, he saw the people praying. And he said, that's a very great vestibular input. So my point is that in the tests that you're doing with animals, they're not allowed to have the vestibular input. And the tapping also is without a vestibular input. And for dance, of course, it's a very important part of dance. So maybe separating it out is a bad idea, and you should try and have the rats. And you can see it in the bird also, where he's bobbing his head. So he's getting, I don't know anything about vestibular input in birds, but it might be a very important aspect to allow the motion of the head and the vestibular input.
That's, again, a very, very good point. We know that the vestibular input gets into the auditory system very, very early. Okay, that's a paper with Yael Vigdorson and Yossi. Okay, so yeah, that could be. Just a moment,
Does the fact that the range of the tempo between up and hertz and 2 hertz is shared among animals and humans tells us something fundamental about the brain, or maybe just a result of the nature of what we call music, which induce this kind of range in order to induce it?
Again, a very, very good point. I tell you my hand waving ideas. I think this has to do with typical motor rates. Animals, mammals at least, can perform actions that are at about these rates. Okay? And the smaller animals have smaller muscles, okay? So they produce smaller forces on smaller masses. But the end result is that you end up with about the same range of frequencies. Actions don't go much above 10 hertz. 10 hertz is I think, a high rate for any animals that we work with. So this range of 2 hertz, around 1 hertz, it's the one order of magnitude below the fastest you can do. I think this is shared across many animals. Basically, the hypothesis is that this relates to the fact that the whole world around us works at about the same masses and forces and velocities and things like that. So the nervous systems and the motor systems are tuned, roughly tuned to these rates. I don't know whether the 2 hertz to half hertz is optimal for rats. Tested them at 2 hertz, or one tested them at 2 to half to 2 hertz, because that's the rate for humans. It could be that rats actually do it better at faster rates or at slower rates, I don't know. But they can do it also at the half to 2 hertz range. I don't expect an order of magnitude difference in the best rates between rats and humans. There may be a factor of 2 either way, not a factor of 2. Hagai?
Yeah, it is more a comment than a question, just to say that this animal called human usually can follow tapping very, very good up to, at least in my experience, up to 6 hertz. So
yeah.
we start at 0.5, we go up to 6 hertz, and we do very good. A patient with Parkinson's disease, we have the Hastening, H-A-S-T, AATSA, I don't have, apology for my dyslexia. Okay, so the Hastening phenomena, where if you start with them at 0.5 hertz, they follow it very, very nice, then up to 2 to 0.5, and then you go from 2 to 3, they stop to follow the metronome, and they jump to their tremor rhythm. So they jump faster, and the idea is that it is a kind of competition of attractor. There is the metronome attractor and the internal rhythm attractor, and when they are close enough, the stronger internal attractor became stronger and pushed them away. So you can play with dopamine system in your model to feel.
So it's not very, Vani now, she just got a position as a Tenutak researcher at UNAM, and part of her research proposal has to do with humans and dopamine and Parkinson and things like that. And that's obvious.
So look for this Essening phenomenon.
Okay, thank you. And please come again next week. It's Alex who's going to talk.
לא אכפת. יש תגובה פשוט חמה. אבל יש לי שאלה יותר קונספטואלית. אין הבדל בין פרדיקציה לבין ריאקציה. ההפרדה שלי מלאכותית. יש לך מערכת ריאקטיבית, אתה נותן לזה אינטרפרטציה. לכן ההפרדה הזאת היא הפרדה...
הטסט הסטטיסטי, בסופו של דבר, הרספונסיב רייט היא רספונס שלה האורך שלה הוא תלוי במקום.
כן.
התשובה שלנו בסופו של דבר היא מאוד קרובה למה שאתה אומר. יש פעולה שהיא טריגרד על ידי הגילוי הקודם, אבל היא תלויה בקצב של הסדרה הנוכחית שלנו. באיזשהו החיה...
ואתה נותן לזה אינטרפרטציה כפרדיקציה.
אני נותן לזה אינטרפרטציה כפרדיקציה כי זה מה שהחיה צריכה לעשות.
נכון.
לקבל את המים היא צריכה...
זה לא להפריד בין פרדיקציה לריאקציה, להפריד בין מודלים שונים של ריאקציה, שאחד מהם אתה קורא
אחד הוא טמפו דיפנדנט ואחד הוא לא טמפו דיפנדנט. אז אנחנו במאמר ניסינו די במדויק להגיד משהו מהטיפוס הזה. בעצם פרדיקציה זה טמפו דיפנדנט behavior, שהיא גם סינכרונייזד למטרום.
אז במובן הזה העבודה של גרמן היא מעניינת, כי אתה מקבל יותר מאחד, יותר מפיק אחד אחר.
כן, זה חוט שדרה שם, נכון?
דטקטום.
דטקטום, כן.
כמובן שגם שם אתה יכול להגיד, ברור שזה ריספונסיב, זה לא...
לא, שם זה...
לא זה לא ריספונסיב.
זה הולך לכיוון של מה שנקרא אינטיימנט. אתה מייצר, הקצב הקבוע הוא מייצר איזשהו משהו שהוא זמנית, מעגל אוסילטורי, שזה הקצב התמוני שלו, ואתה רואה בעצם את הרינגינג של המעגל.
זה מעניין, שאתה יכול לקבל רינגינג בהרבה תדרים שונים. אני לדעתי זה לא...
אז המאמר שלי עם שעווי צ'ן, המאמר מ-2017 עם שעווי צ'ן מראה אותו דבר בקוטקס היסטורי. אבל בקצבים הרבה יותר איטיים.
גם שם זה...
זהו, כן. שם בקצבים מאוד איטיים, כי זה פעולות די...
זה הקלציום אימג'ינג לפני מיליון שנה.
אותו דבר, כן. גם שם, 2017 זה קלציום אימג'ינג. דווקא הקלציום אימג'ינג לפני מיליון שנה היה יותר מהיר מהיום, הסנסורים.
יש לך
מה? של זה? לא.
4 סקנד, 6 סקנד ו-10 סקנד.
מה?
4 שניות.
כן, אז במאמר עם שעווי יש שם שנייה וחצי, 2 שניות ו3 שניות. ואחד מהטסטים שלהם היה שהם עושים את זה אינטרוול של 2, אינטרוול של 3, אינטרוול של 2, אינטרוול של 3 וכן הלאה, אז הם לא ראו